Hi there, let me introduce a method to solve semi-definite programs using projective cutting planes, which is an algorithm that I initially worked in a purely linear context. I come from the world of linear programming, in integer linear programming. Let me first present projective cutting planes for a linear program with prohibitively many constraints. So we have a polytope that we don't know in the beginning. We are on an uncharted territory, as I say, and we have no idea of the constraints of the feasible area. Usually this problem is solved by repeated separation, starting from a solution, and the cutting planes algorithm progressively removes infeasible solution. Let's suppose, for the sake of the needs of this talk, that the point 0 is feasible. More on that later. I propose that the first step of this algorithm to advance towards the direction function up to the point where this projection hits a facet of the feasible area, like this. Okay, so this is a first facet. It describes a first outer approximation of the feasible area, which is this big triangle. Its optimal solution is opt P1 here, so this is an outer solution. If we maximize the value, its bigger, it is an upper bound. And this is a feasible solution on the other side, because this is where we hit the constraint. So this is a feasible point, a lower bound. Okay, what can we do at the next iteration? Notice that all points between 0 and this feasible solution is red are feasible. We take one point on this segment and we project towards the best outer solution, opt P1. This way we discover a new facet of the feasible area, a new contact point, the blue circle, and the new outer solution. Notice that now the inner and the outer solution gets closer. For the sake of the needs of this talk, let's say the feasible area has only 3 constraints. Now I will find the last one by doing this projection. Using this projection, we find a new feasible point and a new outer point. They are very close now. And all that remains to be done is to prove that opt P3 is feasible, which will end the optimization task. For this, it's enough to finish with a last projection from the green square towards opt P3. And here, with this projection, we'll return that opt P3 cannot be separated. In this way, we prove that we can easily prove that the overall method will converge. Why? Because it generalizes the standard cutting planes that solves a separation subproblem on opt pk at each iteration k. So in the worst case, this algorithm will end up enumerating all constraints. What I like about this proof is that it takes only 2 lines. Many people try to use in this kind of work longer proofs so as to show they are clever and smart, but actually the method was designed to be as simple as possible so as to avoid complicated proofs. I started this line of work some 10 years ago. In my first article on it, it was a quite complicated proof because the method was a bit more intricate, more complex. So the most difficult task was to make it even more simple. And if the method is simple, it's easier to implement and also easier to understand, and it's also faster. So in the second work on this idea, I managed to make this proof very, very simple. And one question can be asked now in the context of semi-definite programming. In semi-definite programming, the SDP cone has infinitely many cuts. Okay, I understand this. So this can make this proof more complex. But I'm not a theory guy. I mean, for me, everything on this planet is finite. At least when we speak about computers and not about dreams, in the sense that whenever this algorithm will be implemented somewhere to solve SDP programming, guess what? It will be implemented on some computer with a finite number of bits. So, all along the way, the number of cuts to be considered will be finite. So, in this sense, I can say that for a practitioner, the SDP cone actually has a finite number of cuts, of constraints. I understand that the theory guys won't like this argument, but it's crystal clear that this is what happens in practice. So unless you work on some application where you need, I don't know, a precision, I don't know, of 1000 digits, I don't know, things like that, as long you are okay with approximating the SDP cone with a finite number of cuts, this finite number of cuts will be discovered by this algorithm using the cutting planes logic. Now also notice in black that the inner solutions we considered generate a kind of central path. A central path like in interior point algorithms. I ask myself a question. What happens if I cannot find an initial feasible solution? In this case, I think I will need the interior point method framework to find an initial solution. And I did study it. And another question came to my mind. What happens? There is a huge amount of work in the literature on interior point methods for SDP programming and others. And I always wondered, the inspiration for this idea came from theory, because the interior point method was discovered to solve a theoretical question. And from that point on, there was a huge amount of work in which many respected researchers that I respect a lot try to find the central path using predictor-corrector methods, for instance. And I noticed that many people stick to the interior point method framework. Is this really necessary to stick to it or not? This is a question I asked myself. For the moment, I avoid the framework. Maybe I won't be able to avoid it to find the first feasible solution. What I really ask myself is if this is the good idea to invest such a huge amount of work on sticking to this framework. I wonder if there are maybe there are some frameworks that are easier to handle in practice, but where we may lose all the theoretical properties. Now I move to the SDP area. Okay, let's consider the SDP program written this way. We maximize over the y variables and linear objective function, and we have this matrix X, which has to be SDP. Okay, so X is written this way, where this operator simply sums up AI, YI. This is the classical formulation, and here we have this implication, which says that the dot product between X and this matrix, S transpose, is greater than or equal to 0. Okay, we all know these implications in SDP programming. And from this point on, I will see the SDP cone as a polytope described by infinitely many cuts. But as I said before, when implemented on my machine, on yours, the number of cuts will always be finite in reality. Okay. As I said before, we could address this problem by progressively separating a feasible solution. The standard cutting planes logic is not very effective, at least not in any of my tests, and this is why you won't find a huge number of articles on this idea. I think some people manage to make it work, but it's quite rare. So as I said in the linear programming part, in the new method called projective cutting planes, instead of the separation subproblem, we have the projection subproblem. Given some feasible y here, in the feasible area, what means in the feasible area? That means that the associated x is SDP. What is the maximum step length t star? So that, sorry, there is a mistake here. So that y plus t star d remains SDP. It will be written more clearly this way. We project from y towards some direction d. This requires solving these problems. Max t, so that x plus td is SDP for a given SDP x and an arbitrary d. X, it's this, which is SDP when y is feasible. The direction d may be SDP or not. It's undefined. So what we need to make projective cutting planes work is solving this subproblem. To make it visually easy to see, we want to project from some SDP matrix inside the SDP cone x towards some direction d, so this can be the point x plus d, and here we need to solve this projection subproblem. We need to find t star, so that x plus t star d is SDP, the maximum t star, so that x plus t star d is SDP. At the same time, we need to find the cut. That is a cut that is satisfied with equality by this point. When I say a cut, it's an SS transposed. Okay, let me say that the problem is quite easy if x is strictly SDP, as in this example. But if x is not strictly SDP, it stays on the boundary of the SDP cone, the problem will be difficult. But let me just discuss a bit a very easy to implement approach. So we need to solve this. Notice t star is the generalized eigenvalue of x and minus d. And the generalized eigenvector v satisfies xv equals minus t star d v. I did not have the time to fully investigate this approach, I must confess it, but this is the practical question. We actually need here a very particular generalized eigenvalue, namely the lowest eigenvalue, real eigenvalue above 0. Algorithms solving these problems also have to deal with complex eigenvalues many times. For the moment, I did not find some software that can do it very as fast as I need it. Because computing generalized eigenvalues remains quite difficult, and I'm obsessed by speed. On the other hand, there is a huge advantage: the existence of many of the algorithms that compute generalized eigenvalues. Using this, the projection algorithm becomes very simple to implement, at least in software like MATLAB or Julian. And so the overall cutting generalization of cutting planes can be very easily implemented. Yes, the only question is speed. The main challenge to make all this stuff work is the speed of the projection algorithm. And to speak in down-to-earth terms, to make it work, I realized it should be similar in speed to computing a Cholesky factorization, or computing, let's say, at most the smallest eigenvalue of a matrix. if the speed is closer, for instance, to computing the whole eigen decomposition, any hope will be lost. So speed is all we ever need here, and the complexity theory will not help us too much. The complexity theory will only give an approximation, let's say, a complexity class for the problems, but what happens in real life can be very difficult. This is why I do not express myself here in terms of complexities. What I know is that Cholesky is very, very fast, for instance, in MATLAB, and so is the smallest eigenvalue of a matrix. Because they work on these operations for years, but computing the whole eigen decomposition is crazy. And if we ever, for instance, solve the projection problem by computing all generalized eigenvalues of x and minus d, this is even crazier. I must confess I don't know what the future will disclose, but for the moment I don't think computing the generalized eigenvalues will be a practical solution in the sense of speed. It can be a practical solution in terms of implementation simplicity. So let me discuss a bit the way I did it. We have to project this, and the projection subproblem we will see is quite simple if X is strictly SDP. In this case, there is a unique Cholesky factorization like that, and the K is non-singular. Okay? And we will later see that in this case the following projections are equivalent. If we project from X to D towards D, or from the identity to D, is the same. The T star is the same. Okay? And to have this projection, what happens? Actually, sorry, it's a mistake here. Is D prime from I to D prime, which is the mid term here. So to solve this second version of the projection problem using D prime, we actually need to define this, which is very, very easily because it reduces to computing the minimum eigenvalue of D prime. Thus, the projection computational cost in this case, you need to pay one Cholesky and one minimum eigenvalue, which is very, very good for me. The projection is more difficult if X is not strictly SDP. Yet, even this simplified SDP case enabled me to solve some particular instances very, very rapidly. I mean, just when I started the project, I gave a very simple instance in the sense that I knew that some epsilon identity is feasible. We have, for instance, 11 y variables, the matrix size is 400. All eigenvalues of the AI matrices are positive, and so are the eigenvalues of C. This comes from this constraint, okay? AI and C. And this was the very first instance that I managed to solve. So the blue stuff are the upper bounds of the standard cutting planes. I needed almost 10 seconds. Mosek solved it in 7 seconds. The Koenig bundle solved it in 2 and 23 seconds. And the advantage of the new method is that it provides both lower and upper bounds, because we converge towards the optimum using both inner solution and outer solutions. And you can see that it was solved in a bit more than 1 second, but using both the lower and upper bounds, actually the story was finished after 0.5 seconds. What I want to say is that, generally speaking, let me say that the projection X to D can be calculated more rapidly if D belongs to the image of X. Okay, this means that if I have a null vector D of X, it's also a null vector of D. And in this case, it's easy to project. Of course, this property will be satisfied when X is strictly SDP. But even if it's not strictly SDP, this simplified setting will make it work. What is nice is that projective cutting planes can touch a bit at the inner points to make it. It may be a feature, but it may adapt its own evolution to seek such a property. Let me just discuss the most simple case. The full paper is online where I discuss much more complicated stuff, but here I just want to send the main message across, and this is the only slide with more theory to prove what I said before. It's not very complicated, but when you are first looking over this, I cannot go more deeper into detail. So I have, let's say, X is SDP, okay, and the previous property will hold because the image of a non-singular X is the whole space. We apply the Projective factorization. We have X written this way. D will always could be written this way because K is not singular, and it's very easy to find the D prime by back substitution. This may require this complexity, but what I said before, MATLAB is able to solve these questions much more rapidly in practice because K is triangular. Actually, I almost find zero relation between the theoretical complexities of different operations and what I see MATLAB is doing, because of all sorts of streamlined, optimized operations. So we can rewrite this question like this. I replaced X by the Projective factorization. I have the identity here. I replaced D with this, and we need to find the maximum T so that this stays SDP. But these two matrices will be congruent using K and K transposed, so this is equivalent to solving this. And the step length, if you take 1 minute to think about it, is -1 over the minimum eigenvalue of D prime, unless D prime is SDP. If D prime is SDP, of course, T star is infinity. And then I have more slides about more complicated cases. And if you are looking over this video, you may have the time to look over them. But I have the paper where everything is described. I needed the LDL decomposition. It's more complicated than when X is on the border of the SDP cone. Now I have some results, but they are very boring. I don't like when I see tables during talks, so I won't show you much tables. What I want to show you is the code. So I implemented this almost. This is another software. I have almost still another software. I'm sorry. SDP is here. I almost have 4,000 lines of code, and I will execute for an instance with K is 20, N is 400. I have some null vectors when I define the matrices A and C, but generally, for instance, when I generate the matrix C, it will have C is a matrix that has an eigen decomposition, and the eigenvalues are between 30 and 50, and some null vectors. This means that the matrix C is not strictly SDP, it has some null vectors. Okay, so now I will execute this using Mosaic. Okay, so you notice that because we have many complex operations here using interior point methods, it takes about 10 seconds on my machine, and this is the objective value. And now I will solve it the same instance with projective cutting planes. Now we generate cutting planes here. If you have time, these are cutting planes. This is the outer solution, the pierce point, the hit point, and other information. But eventually we end up with the same solution. But it took 1.5 seconds. Exit A means that out of the 79, I think, iterations, I think I have 79 iterations, 72 of the 79 iterations could be solved. The projection problem, subproblem could be solved using the very simple case I presented in the slides. There are other cases where that was not enough, but most of the time that was enough, and that was very fast in this case because I only use Cholesky on the minimum eigenvalue of a matrix. So I don't know if I still have anything useful to say. Thank you for being with me today, and here some more results in using a table format if you want. Have a nice day.